So today we're going to cover net area and the fundamental theorem of calculus. So let's get into it. So think of calculus like looking at the coastline. The x-axis is your water line, and anything sticking above the water is like a mountain. So we count that as positive area. So anything dipping below the water is like an iceberg. We count that as the negative area. So when we talk about net area or a definite integral, we're just looking for the grand total. So if your mountain is huge but your iceberg is small, you have a positive total. If the iceberg is bigger, your total is negative. It's basically just a balance sheet of what's above and below the line. So now how do we actually calculate the total? So we use what's called the fundamental theorem of calculus. Think of it as the magic key. Instead of trying to measure every tiny curve, you just find the variant function of your shape. You look at where you ended, which is the point B, and look at where you started, which is the point A, and subtract that 2. That's the difference. That difference gives you the exact area of everything in between. So it's like your GPS.
Because our function is straight line, it creates perfect triangle. So we can use basic geometry, which is area of triangle 1/2 times base times height to find the area before we even touch calculus. So first is we're going to need to find our water line. So our water line is in the x is equals to 2. So that is our water line. So it creates the half of our shapes. So next is we're going to need to find is the underground iceberg, which is we have the base of 2 and the depth of -4. So we're going to use the area to find the area of that, which is half of 2 and times -4, we have -4. So in the right side we have the mountain, which have the base of 2 and the height of 4. So the area of that is half of 2 times 4, we have 4. So in summary, we're going to need to find the area. We're going to need to add those two. So we have -4 plus 4, we have 0. So this is exactly our net area.
We're going to prove that the geometry specialist was actually correct, and we'll do that using the fundamental theorem of calculus. So what we need to evaluate is the definite integral from 0 to 4 of 2x minus 4. First step, find the antiderivative. In simple terms, we're looking for a function whose derivative gives us 2x minus 4. Using the reverse power rule, the antiderivative of 2x is x squared, and the antiderivative of -4 is -4x. So that gives us f of x equals x squared minus 4x. Next step, we evaluate this from 0 to 4. Let's start with the top bound, which is 4. If we plug that in, we get 4 squared minus 4 times 4, that's 16 minus 16, which equals 0. Now for the bottom bound, which is 0, plugging that in gives us 0 squared minus 4 times 0, so that's just 0. Finally, we subtract the two results, so it's f of 4 minus f of 0, which is 0 minus 0, giving us a final answer of 0, so the net area is 0, and that perfectly matches what we got using geometry earlier, which basically confirms that both methods agree.
To master this topic, you must understand the critical differences between net area and total area. So let's use a real-world analogy. So a net area or displacement, imagine walking 4 miles east, which is +4, then turning around and walking 4 miles west, which is -4. How far are you from your starting point? Also, which is +4 and -4, it equals to 0 miles. Calculus computes net area by default. Positive and negative regions cancel each other out.
Let's compare that to total area. Think of a fitness tracker. It just records how far you walked. So instead of canceling, it adds everything. 4 miles plus 4 miles equals of 8 miles. This is what we call total area. We treat all values as positive using absolute values. That's why in the graph we saw, the net area result is 0, but the total area is 8. Even though the graph has equal areas above and the below axis, the definite integrals cancels them out, while the total area adds them. Here's some expert takeaway. The net area is equal to the displacement with direction and can cancel. And the total area is equals to distance. No direction, always positive.